So, good evening, everyone. I am Calvin Paul Joseph, and today I'm going to conduct a week 11 problem solving and doubt clearing session for the course State Space Approach to Control System Analysis and Design, taught by Professor A.P. Tiwari of IIT Mumbai. And the outline of today's session will be I will be talking about what sir has discussed basically this week, that is about the nuclear power plant, how there is a non-linear model of fifth order for the nuclear power plant, and how when we want to use the methods of linear control which we have studied in this course, we have to linearize that model around a particular operating point. And after that, the sir has checked what is the controllability and observability of that linear model, because we need to know that information is critical for us. And once it was proved that the system is controllable and observable for the determinant is greater than zero, that is the neutron density is greater than zero, then sir has used the concept of output feedback to design a controller for the system. Okay? So we will be looking into these aspects. So let me open the PDF that sir has shared. He has considered this. He has discussed about what is in the nuclear reactor. So he told that the nuclear reactor is basically for controlled fission. Fission is like breaking of the nucleus and disintegrating the neutrons. Whereas fusion is when you fuse two atoms together. So in our case, in the case which sir is considered, the nuclear reactor is basically for a controlled fission chain reaction statement. It has to be under control. If there's a lot of control, then the power plant will be damaged, and then the radioactive should be dispersed into the environment, and that would be very harmful, and it is going to be safe. Okay? So mostly the uranium-225 nuclei is used for undergoing fission. Okay? And it releases approximately 200 mega electron volt energy for fission. Just for the number. So this is the block diagram for nuclear power plant, where if you will observe, for this entire thing is your reactor. And these green things, these are your control rods. And you have a control rod system, which work is basically so. The work of that is basically to control the neutron flux density. And there's a filling chamber which has a neutron flux detector, which will detect how much is the neutron flux in the chamber. Okay, that information goes to an amplifier which will generate some signal. Okay, that signal can go for monitoring and control, or there's power measurement and calculation can be done, and that will go to control rod drive system. So the control rods are basically controlling the neutron flux density inside this nuclear reactor. So there's a coolant also which is present. So the objective of the coolant is it will take the energy, the heat energy which is produced during the fission reaction. It will absorb it and it will pass it to the steam generator, which will send that to the steam, and that will move the turbine. And when the turbine moves, there's an electrical generator which will convert that power to electrical power. So this is how nuclear reactor is used, and nuclear power plant is used to generate power. And this is the overall block diagram which you must consider. Okay. So nuclear power stations were operational from the 1950s. Nuclear energy was about 10% of world's electricity from about 444 reactors. So some of this is important for you guys to remember because certain theory questions might come in the exam, certain executive questions. Okay. There are 16 nuclear reactors under construction and commissioning. And in India, there are four. Okay, first commercial one is in Tarapur, Maharashtra. In 1968, in India, the 23 reactors are operational, producing 7.5 gigawatt electricity approximately. There are four research reactors. The research reactors mark two is at BRC Trombek and the IGCR Talpakam, okay, which is close to Chennai. So these are used for isotope production and research. So there are 23 power reactors and four research reactors. So these are separate research ones in which we are producing isotopes and it is used for research. It can be classified as fast reactors, thermal reactors, and the fast breeder test reactor. Kalpakam is the only fast reactor operational now. You should, okay. All other reactors are thermal reactors. So based on the coolant, it can be liquid water cooled reactor, heavy water cooled reactor, gas cooled reactor, liquid metal cooled reactor. So the core consists of the fuel, it consists of the moderator, it consists of the coolant, it consists of a control rod slash elements. It has a reflector, there is a shield, there's a neutron fluid, flux sensors. It can be internal or external. Right. So when fission occurs, the neutrons get fall into two categories. So one can be prompt neutrons, which release within 10 to the power minus 4 seconds of fission. These are delayed neutrons which are produced due to radioactive decay. So what is done is, because you cannot say each and every reactor, consist for each and every neutron, what is done is we group the neutrons together and we consider the overall behavior that group of neutrons. Okay? So they consider rate of neutron absorption, rate of fission reactions, rate of production of prompt neutrons, and rate of production of delayed neutrons, etc. are considered. And mu is the total neutron yield for fission. So for fission, this much the neutrons are there. Out of that, one minus mu into 1 is because the prompt neutrons per fission, and the rest are delayed neutrons. So there are prompt neutrons and there are delayed neutrons. And so first is neutron absorption is also taking place. Fission reactions are also being produced. There's production of prompt neutrons are there. There's production of delayed neutron sequences. There's neutron data. There's rate of fission reactions. Okay. And this is the rate of production of delayed neutrons is lambda into psi, where phi involves the neutron flux we have to go in second phi of t. To be lambda to phi. So what is the time rate of change of neutron density? Which is mu to 1 is beta fission reactions minus the rate of absorption plus lambda into phi of t. Okay, lambda into phi of t, rate of production of delayed neutrons, which is given by this. So there are some approximations are considered and certain values are taken, which value when you reach this. So this is the rate of change of neutron density in the core, which is given by k minus 1 minus beta 1 L upon k beta t. So this is rho t is called the reactivity, and L star L upon pi is called the prompt neutron generation time. Okay, this gives the rate of change of neutron density as written like this. Okay. It's mathematical. After the implementation of the mathematical model, linearization was carried out with the different model and in one place. Then the controllability study to finally to the output feedback. So yeah, well, there are various theory for nuclear reactor which we are more considered with the mathematical model. The first one is rate of change of neutron density. In the equation neutron that is given by this expression between meter t upon dt. This is equal to rho t minus beta upon a star t minus beta upon a star into meter of t plus lambda into 5. Okay, this is the first equation. This is the first equation we have. So rho equal to k minus 1 is called the reactivity, and L star 11 k is called the prompt neutron generation time. So these are certain constant values we have considered in our stuff. Okay, variations in reactivity leads to variations in neutron density in the reactor core. Okay. Now, what is the time rate of change of delayed neutron precursors concentration? So the delayed neutrons are made produced from the delayed neutron precursors. And if their concentration changes, what is that effect? So that effect is written by this. Time rate of change of delayed neutron precursor concentration. So the rate of change of delayed neutron precursors, which is given by d phi t dt, which is equal to beta upon L star neta t, beta upon L star neta t minus lambda into phi t. So this is equation 2, which we have got. Now, what are the further equations? So till now, it consists of two equations: time rate of change of neutron density and the delayed neutron precursor concentration. Okay, rho t is the input. Rho t is the input which is there. Beta, gamma, and L star are parameters. For uranium-235 fuel water-cooled reactors, these are the values. Beta is equal to 0.0065, lambda equal to 0.08 second inverse, and L star equal to 10 raised to minus 5 seconds. Okay, these are the values. So now, measurement of neutron flux density. How do we measure what is this neutron flux density? So to measure that, there is an associated amplifier which produces a voltage wave. But there will be a delay. It will not be instantaneous. It has certain delay. So this is a neutron density, and this is the sense value of that. Beta is kn upon 1 plus s into tau. Okay. So what we have is measurement of neutron flux density. Well, this we are measuring. So V N of T upon meter Vn upon meter is given by Kn 1 plus S into tau n. Okay, there is an amplifier which has some filter and it slows down the measurement. Okay, so when we write it, what do we get? If we cross multiply, we get Vn plus S tau n is Kn into meter of T. Kn into meter or Vn of T plus tau n into dVn T upon dt is Kn into meter of T or dVn of T upon dt is equal to minus 1 upon tau n Vn of T plus Kn upon tau n into meter of T. Here it's shown over here. Minus 1 upon tau n Vn of T plus Kn upon tau n meter of T. So this is the measurement of neutron flux density. So measurement of neutron flux density. So we have seen three equations. Now let us see the further equations which come up. Now measurement of d neta of dt. We want to produce a signal proportional to the rate of change of neutron density in the reactor, which is actually generated by differentiating V. Okay. So Br is a signal proportional to the rate of change of neutron density, and its transfer function is given by this. Okay. This is measurement of dn of dt. Okay. Hmm. We want to measurement rate of change of neutron density. Which is P upon dt. I want to measure this. So till now what I have is I have Vn of t. My Vn of t is proportional to neta of t. Kind of. In some way, in steady state, Vn of t is proportional to neta of t, but not actually during transient because there's a certain phase lag which is introduced for the phase. So if I want to measure d neta of t upon dt, I need to measure d Vn of t from dt. And this actually is equal to my Vr of t. Okay, this is the Vr of t. So now Vr is a signal proportional to the rate of change of neutron density in the reactor, and it is generated by differentiating Vn. That is true. Plus, we will add a filter. Because you cannot actually implement a practical derivative will require a filter in there, which it will amplify the noise. Okay, so we have Vr of s on Vn of s is equal to Pr of s, Kr of s, 1 plus s into tau r. Tau r. So Vr of s plus tau r into s into V r of s through kr into s into V meter of s, Vn of s. Now, how do we further simplify it? So we want dVr by dt. So we have tau r into dVr t upon dt is equal to minus Vr of t plus k r into dVn of t upon dt. So we have dVr of t upon dt is equal to minus Vr of t upon tau r plus kr upon tau r into dVn of t upon dt. Okay. Now what is that is this Vr of t is increased by Vr bar of t plus kr into tau r into Vn of t. We write assume Vr of t is equal to Vr bar of t, Vr bar of t plus kr upon tau r, kr upon tau r into Vn of t. So what do we get? This dVr of t upon dt is equal to dVr bar in t plus kr upon tau r into dVn of t upon dt, right? So we get so what we can write is this dVr by t upon dt plus kr upon tau r into dVn of t upon dt. This is equal to Vr of t is minus 1 upon tau r Vr bar of t plus kr upon tau r into Vn of t. So we get and plus kr upon tau r into dVn of t upon dt. So this and this get cancelled. So we get d of Vr by t upon dt is equal to minus Vr by t 1 upon tau r minus kr upon tau r square into Vn of t. Okay, so this is the equation which we have got. So by some hook or crook, we have made sure that it is not represented in terms of Vn of t, it is represented in terms of Vn of t. So this is some certain mathematical manipulation which was done. Okay. Now there can be reactivity variations. Variations in reactivity rho are affected by moving control rod out or in its respective equilibrium position by means of a motor. So those control rods are driven by a motor. Okay. That has been the CR position measured with respect to its equilibrium position then rho equal to k rho h, where k rho is equal to 0.025 kPa. The variation in h are affected by applying the control voltage V. We will neglect the time constant of the drive. So we'll assume that the motor time constant is very fast, so that can be neglected. So dH upon dt, variations in h, are affected by applying the control voltage V. So the equation is reactivity variation. V is reactivity variations, where we write dH of dt, dH of t upon dt is equal to Km into Vt, Km into Vt, where Vt is the control voltage, which is applied. So this is the thing. When a nuclear reactor operates on power, the temperature of the fuel, coolant, monitor, and such material in the code rise well above the room temperature. The number of fission products which absorb neutrons are produced, and fuel nuclei reduce in number due to drawing. Okay, this phenomenon introduce reactivity variations. So there are variations in reactivity. However, these are ignored in the study of the reactor. So these complex phenomena which are required to accurately model are not considered. We just consider some constant value. Here there are certain plant systems also which are not considered in the model. So this is the final set of equations. So d liter of Q of dt is equal to, let us see what we have. Rho t minus beta on L star into meter of t plus Qt is having kp into k rho into h. This is a k rho into h of t minus beta upon L star into meter of t minus beta plus number of t. This is given by this equation. dVn of t measured neutron flux density, and this is the derivative of the neutron flux density proportional to that, and the rate of change of what? Right, the products, the position of the products. Rho equal to kp into h, Vr is equal to Vr dot plus Pr upon tau into Vr. So these are the parameters which are considered. Let us write the overall set of equations. Set of equations are written like this. It is d meter of t of dt, d meter t dt is equal to k rho h of t minus beta upon L star, beta upon L star meter of t plus lambda into 5 of t. Lambda into 5 of t. Now d 5 of t upon dt, this is equal to beta upon L star meter of t, beta upon L star meter of t minus lambda into 5 of t. This is one case. Then d of Vn of t from dt, this is equal to minus 1 upon tau n Vn of t minus 1 upon tau n Vn of t plus Kn upon tau n Kn upon tau n Vn of t. This is the next set of equations. Then dVr by t upon dt is equal to minus Newton tower R VR bar of T minus KR upon tau R square minus KR upon tau R square into Vn of T. Vn of T. Okay. Then further, pH of T upon dt is equal to Km into V of T. So dH of T upon dt is equal to Km into V of T. So V of T is our input. With dH T of dm of T is our input. So another equation is equal to kph, k rho h. We have equal to k rho h in PR bar is equal to VR plus V so VR bar plus PR upon tau VR. K PR upon tau R into Vn. This is the formula for VR. So now, and these are some parameter values which are given, which we consider. Model order is 5, number of inputs is 1, number of outputs are 2. Okay. This is one output row, VR is another output. And it is a non-linear. Why is it non-linear? Because this part, this multiplication into this multiplication is there. So this is what is causing the non-linear. So all the other equations are linear, only this part is the non-linear equation, which has to be considered very, very carefully when we do our analysis. So at steady state, all these differential terms is d over these terms. This time rate of change of neutron flux density, time rate of change of the precursor of the delayed neutrons, time rate of change of this sensed rate of change of neutron flux density, sensed derivative, this time rate of change of height, all these will become zero in steady state. And then we have some steady state value. Suppose the neutron flux density was meter is Newton naught, which is meter d, which is the demand. And this is the time rate of is the uh, delayed precursors value. And Vn of 0 is k into Newton. Which is Vr 0 is equal to 0. Which is Vr 0 bar is k upon R square V into 0. Okay, rho 0 is 0. And hence H 0 is equal to 0. Okay. Demand can be any value in the range of 0.9 to 1. So it is modeling for different H values. What are the eigenvalues for the system? Has been considered for different H values. And the behavior of the system also has been shown over. These are the publications and certain stuff which you can read for the understanding. So this is the nuclear reactor steady state. Let us see now what is done for. Now we are considering case study of the nuclear reactor and model development. We are trying to develop a linearized model of this nuclear reactor. So first, what will happen is the nonlinear model will be linearized. The linear model will be put in a standard state space form. We'll do the stability, controllability, observability. We will try to understand it. And then the transient response of the system will be obtained and compared with the nonlinear system performance response. Okay, so these are the set of differential equations we got, and these are the other set of equations. Let us say these are the steady state equilibrium operating conditions. And we will we linearizing it around the steady state. About actually small changes in the value of the inputs. Well, let us consider this. So now so we are trying to find a linearized model around that operating point. So what we do is this beta of t will actually beta 0 plus delta and beta plus delta equals 2. This consider steady state operating points. For steady state, beta naught is equal to beta 0. Okay, and for this rho beta upon h star beta upon h star beta naught upon lambda. This is our this is the rho this one here. Over beta naught 0 big K and over beta naught we are 0 so we are 1. Yes, we are upon tau square b equals. We have BR, so we real is PR upon tau R bar. The minus PR upon tau R is PR 0 bar actually is equal to minus. So now this is also minus. Don't try. We don't know what shade is considered. Let us check further. And rho naught equals 0 and h naught equals 0. Okay. We have rho naught is equal to 0. H naught is equal to h naught is equal to 0. There is a change in the operating time. So this nonlinear equation will linearize around the steady state. I think small changes in the value. So there are certain small changes in their values. So what we will do is we will consider beta t is actually equal to phi of t is equal to phi naught plus delta phi of t. Then P of t equal to a naught plus delta dn of t. Then V r of t, V r bar of t is V r bar plus delta V r bar of t and h of t equal to h capital H over h naught plus delta h of t. So these are what we substitute. So what we will get is, and this h naught is 0, so h of t is equal to delta h of t, right? So what do we get is, first set of equations. Let us consider the equations. So we will do first equation d of dt neta plus delta neta of t. This is equal to kp into h of t. So kp into 0 plus delta h of t minus beta upon L star into neta naught plus delta neta of t plus lambda into plus lambda into phi of t plus phi naught. So this can be written as d neta naught upon dt is equal to, so d neta naught upon dt plus t of delta neta t upon dt is equal to kp into delta h of t minus beta from L star into neta naught plus delta neta of t plus lambda into phi of t plus lambda into phi naught. Now, there are two terms. We can write d neta naught upon dt, which is equal to 0, which is actually equal to kp, which is actually equal to minus beta upon L star into neta naught plus lambda into phi naught. Okay, this is equal to 0. This is one part. This is the average quantity. Average quantity, or we can say the steady state quantity. And this d delta neta t upon dt, this is equal to kp into delta h of t upon L star into neta naught minus beta upon L star into delta neta of t plus lambda into phi of t, and an additional term plus kp into delta h of t from L star into delta neta of t. So this is the second order term. And what is considered is that delta h of t is much smaller than h, and delta neta of t is much smaller than neta naught. So the product of these two small quantities is negligible. So we ignore it. So it is ignored under assumption of small variation. So we write d delta neta t upon dt is equal to kp upon L star into neta naught into delta h of t minus beta upon L star into delta neta of t plus lambda into phi of t. So this is the equation of our first, this is our first equation. So accordingly, when we see the A matrix, it has this term, and this term. But now let us consider for all the other cases. If you observe all the other equations, these are all linear equations. So when we do the perturbation and linearization, we will get the same equation only in perturbed form. So what we will get in that case is we will get equation 1 Equation 2 is, what is equation 2? This actually, I'll just show for one case, then we will consider it next. D of dt of phi plus phi naught, that is the average value, and the delta of phi of t. This is equal to beta upon L star, beta upon L star into neta naught plus neta of t minus lambda into phi of t. Lambda into phi naught plus delta into phi of t. The delta into neta of t. This equation will be d phi naught upon dt plus d delta phi naught upon dt. This is equal to beta upon L star into neta naught minus lambda into phi naught plus beta upon L star delta neta of t minus lambda into delta phi of t. So this, so we equate the steady state and product quantities, we get d phi naught upon dt is equal to 0. This is beta upon L star neta naught minus lambda into phi naught, and d of delta phi t upon dt. This is equal to beta upon L star into delta of neta t minus lambda into delta of phi of t. Okay, this is the second equation. Similarly, for the third, fourth, fifth equation, we can just write the same. We are interested in this linearized, perturbed linearized equation. We are mainly interested in that. So what do we do is the third set of equations we write it as d of delta Vn of t upon dt. This is equal to minus 1 upon tau n minus 1 upon tau n delta of Vn of t, and then plus kn upon tau n plus kn upon tau n delta neta of t. This is the third equation. Similarly, the fourth equation can be written as dvr delta d of delta vr bar of t upon dt. This is equal to minus 1 upon tau r minus 1 upon tau r d of vr bar of t plus minus minus k r then tau r square into Vn of t. Vn of t. Okay, the fifth equation is given by dh of t upon dt. dh of t upon dt. This is equal to this. Sorry, this will be d of delta h of t upon dt is equal to Vm into delta of v. V into delta of v. Delta of v of t. So, if you will again look back, these are again the linearized set of equations, and we write it in this form. X dot of t is equal to ax plus bu, where these are the states and this is the output. These are the states and this is the output. So, when u is delta v, So we get A matrix is given in this form, B matrix is given in this form, and C matrix is given in this form. Okay. We write it as. So basically, we converted the nonlinear model into a linearized model. First, we wrote the nonlinear model where each derivative was a function of it's a linear combination of the states, not exactly a linear combination in the first derivative differential equation. It was a non-linear combination. Then we linearized the first equation around a dead steady state operating point, and we got a set of perturbed dynamical equations. Then for the second to fifth, it is already linear, so the perturbed equations are same as the earlier equations as well. And then we can write what is known as the A matrix, B matrix, and C matrix. So one thing I'd like to stress further is my delta rho. That is outputs. What are the outputs? Delta rho. This delta rho is equal to Kp into delta H. Kp into delta H. And my delta Vr is equal to delta Vr bar plus Pr upon tau delta Vn. So this is the output. This is delta Vr bar plus Pr upon tau into delta Vn. Okay, it is given in this form. So there are the linearized equations is arranged like this, and we get the corresponding ABC matrices. These are the eigenvalues of the linearized system around these particular operating points. So we'll consider what they have done. First, I'll just show what I've written for the ABC matrices. So let us open up and check. So this is the A matrix. So I've written the code for ABC matrices. Let us run the section. Let us re-verify our code and check whether it is correct. So A is given by minus beta upon L star, then lambda 0, 0, then Kp to eta naught upon L star. Fine. This is given by B upon L star minus lambda. So this B upon L star minus lambda, then 0, 0, 0. Then you have 0, 0, 0. Then this is Kn upon tau n, Kn upon tau n 0, minus 1 upon tau n, minus 1 upon tau n 0, 0. This 0, 0, minus Kr upon tau r square, minus 1 upon tau r and 0. Minus Kr upon tau r square, minus 1 upon tau r and 0. The last one is all 0, 0, 0, 0. Okay, this is where all are 0. The B matrix is given by all four are 0, then followed by Km. Followed by Km. And C matrix is 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, and then 0, 0, Kr upon tau 1 and 0. It is same. So using the power of symbolic math toolbox and correspondingly the uh, like initializing the variables in this format, we can have a code visual representation of our linearized system. Like I found it difficult to find L star, so I written it as L subscript star. But perhaps if you want to make it into latex equations, you have to take it into latex software and replace L star by the L star actual L star. Okay. Now we have to check the controllability and observability. Yes, do what is Q is controllability matrix A, B. Let us see how it looks like. Okay, it's gonna be done. Okay, let us actually do Q is B and A. B. This is the overall large Q matrix. Let's find rank of Q comes out to be 5. Okay, so it is controllable. There are certain conditions which you look. So if you will observe this controllability matrix, first of all, to compute it will take a lot of time. For one to do 5 cross 5, this in software it is easy, but if you have to do hand calculations and analyze the controllability, which is actually what you would have to do in the exam, then how would you move forward? So that's what I explained, but I just want to show that if I do this two matrix multiplication B, A, B, A into B, triple A into B, 4A's into B, and this is the two matrices you get. And if you find the rank of Q, it comes out to be 5. That is fine. But how do we, compute such a matrix? Do we have to compute such a big overall matrix and then check whether the system is controllable or not? Or is there any other alternative? So let us look at search method which he has considered for determining the controllability. So let us see. So these are the, so let's reorder the state variables. What he has done, dvr bar dvn is written like this. This d change in the this concentration, d meter derivative of that delta H derivative is given like this. Now, last signal depends only on the input signal. This depends only on the input signal. So, system will control this system if this system is controlled. Now, if this system is controlled, then it can be controlled. So, this system is controllable. Subsystem also is controllable. So we need to have the neutron flux density need to be greater than 0. So Q matrix determined of Q comes out with this and the ranking Q is fine. So what Sir has basically done is this was my original set of equations. But what we need to realize is that this fifth state is only controlled by the output, and this fifth state impact is there in this first state. The first and second, and this first state impact affects the second state. So fifth state controls first state controls second state, and the first state also controls the third state. And the third state has impact on the fourth state. So thus we can say that the overall system is controllable. And this can only happen if this meter naught is greater than 0. If this meter naught is 0, then it is no longer controllable. What if meter naught is less than 0? This is not possible because the neutron flux density has to be greater than 0. It cannot be negative. Okay, that's how we can understand that meter naught either can be 0 or can be greater than 0. And because if meter naught is 0, then there's no impact of the fifth state on the first state. There's no impact of control input on the first state, then we lose control. So for ensuring that the system is controllable, this meter naught must be greater than 0. Okay. So that's why Sir has reordered these states into this format. also shown. Let us consider the analytical proof of observability. So these states have been reordered in this format. And then these are corresponding system equations, these are corresponding output equations. We have to find this A hat transpose C transpose. Okay, this is the set of equations written in this form 0 and H2. Okay, these are the variables. F2 and H2 is controllable. Let's for a check. Okay, if you for control the matrix and P is for the observability matrix. And we have seen that is the C what has been done. So we will consider the observability condition. What do we have? T neuton dot d delta phi dot delta h dot. So we get it as delta theta dot delta phi dot delta h dot delta vn dot delta vr bar dot. This is equal to minus beta upon L star lambda Cp into meter naught upon L star. Let us be written to be in a better format if this was done. Let us do the whole linearized non-model. Now we do a section. So it's the observability condition. We will try to find it. So here is A hat. This A hat is equal to minus beta upon extra lambda This here. Then KP eta naught element. This KP into eta naught into L star, comma 0, comma 0. This is the first layer. Then minus beta upon L star again. Minus beta upon L star. Minus beta upon L star. Then minus lambda, comma 0, 0, 0. Comma 0, comma 0, comma 0. Then we have all 0, 0, 0, 0, 0, 0, 0, 0, 0. Then we have kn upon tau. So we have kn upon tau. Then 0. Then you have 0. Then you have minus 1 upon tau. Then what do we have? Again 0. This is there. Then we have 1, 2, 3 zeros. 0, 0, 0. Then we have minus k upon tower square and minus 1 upon tower. So this is the one. This. Where is numbers? Where is separate errors? So this is our A hat. A hat is minus beta upon L star lambda. KP eta naught upon L star 0, 0. Then beta upon L star minus lambda 0, 0. All zeros. Then kn upon tau 0, 0 minus 1 upon tau 0. Then triple 0 minus k upon tau square and minus 1 upon tau. So this is our A hat is correct. Let's go to our B hat. Our B hat is 0, 0, k underscore m 0, 0. So this is our B hat. How it comes, B hat is given like this. And what is our C hat? C hat is equal to 0, 0, 1, 2, 3, 1, 0, then 0, 0, 0, KR upon tower and 0. KR upon tower and 1. So let me run this. What is our C hat? 0, 0, 0, 1, 0, 0, 0, 0, KR upon tower and 1. So let us see what they have done. They have first found out A hat transpose, C hat transpose. So they did. So we have proved this, or we will comment this out. Not commented out, we will not let it display. We had A hat transpose, so A hat transpose. Then C hat transpose. So C hat transpose, C hat transpose. Let us run this section. So this is our A hat transpose, and this is our C hat transpose. Now, this is minus beta upon L star, beta upon L star 0, k and tau 0, lambda minus lambda 0, 0, 0, kp eta naught L star equals 0, 4 zeros. So this is the same. This is the same. C hat also we got. So now we will divide it into these ones. So what happens is F11 0 A hat transpose 1 row third column 1. This is our F11. Let us run it. This is F11. Okay. What is F12? F12 is equal to A hat transpose 3 rows and the fourth and fifth column. So this is F1. Then we have if this is all zeros. So F21 is equal to we have transpose four rows of column, first row, third column, and F22 is equal to we have transpose fourth row, and then fourth row, fifth row. So this is our F11, F12, F21, and F22. Once we have got that, then our H1 is we have transpose from it. It has all the columns. All the columns are to be considered, but the first and third column, first and third row. Okay. Similarly, H2 is here transpose in the fourth and fifth column. We will run this section. So this is our H1, this is our H2, which we have got. So let us see F11 is given like this. Then our F12 is given here 0 time, yes, correct. F21 is 0, F22 is minus 1 upon tau 1 minus k r upon tau r square 0 minus 1 upon tau r, correct. H2, H1 is 0, H2 is 1, k r of tau r 0, 0, 1. Okay, H2 also is correct. Now what should we do? We have got this. If you see F22, H2 is controllable. If you will check the overall system, this is our overall system. So let us check F22 and H22 controllable. How is F22 and H22 controllable? So F22 H2 is equal to H2 comma F22 into H2. Let us run this section. Comes out like this. And you can see that it is a controllable one. Let us find the value. This finally ran 252. So it is a controllable one. Right? Next, F2 H2 is controllable. For the F11, F12 to controllable, this. Okay, let us do that. So controllability of F11, F22 is equal F12 is equal to F12, comma F11 into F12, comma F11 into F12, F11 into F12. It is on the section. So comes out to be like this: scale upon tau 0 minus beta upon h star k and k1 minus. There's some mistake. What is the F11, F12 controllable? This happened. What is this? F11, F12. F11, okay. F12, this matrix is not required. It is not needed. This column is not because it is all zero, so its effect is not there. Right? So what we can do is instead of F12, we will all the rows and the first column. Okay, all the rows in the first column. Similarly, we do here all the rows and the first column. So if we do that, you will get this. K in tau n minus beta upon L star Kn into beta upon L star into tau n minus beta of L lambda Kn of tau n. This is minus Kn into lambda square tau n plus beta into lambda upon L star into tau n. And 0 Kn Kp K tau n of tau n L star minus Kn Kp beta naught into beta into L star square upon tau n. Okay. What has gone wrong is this minus sign is not there. So what is this rank? If so, Kn is positive, Kp is positive, L star is positive, tau n is positive. So only neta naught we don't know exactly what it will be. If neta naught is 0, then this whole row will be 0, and then our system is not controllable, right? So this is how we can get. That's why the condition has been proved that for controllability, neta naught should be greater than 0. And physical significance is neta naught has to be greater than 0. It cannot be less than 0 because you cannot have a negative neutron flux density. Okay, so this is what has been proved. Okay. So observability matrix for the first output. When we only consider delta being, what do we get? Observability matrix for first output. In that case, we have C1 transpose. Okay. C hat first one. So we have P1 is equal to C hat 1, or we can take C hat transpose 1. C hat transpose 1, and then we do P hat transpose. P hat transpose into C hat transpose. Let's consider this. We have again we have transpose here. And we have this over here. Let us run this section. We will C hat transpose into C hat transpose 1. This occurs. C hat transpose 1. C hat transpose the first row. That should be the first row. Transpose into C hat transpose 1. Doesn't matter. So it should be C hat transpose 1 into A hat. This one. So this is one. Okay. should be y1 is 4. 1 is not required. This is naturally. What is here transpose size of here transpose 505 size of C had transpose the first one. The first the C size of C had transpose 5 rows and 2 columns. What is C had transpose 1? C had transpose 1 is just this. So we want the first column, sorry, it's not the first column. This should be from let me set this. So this comes out to be like this. So this is the correct way. So this from 1 column from our 1 column 1. So let us run this section now. So this is the large over P1 matrix which we get. And if you'll observe that its rank is less than 5. So it is not observable for the first output. So this let run like this, let us check. No, it's not running. What about the commas? Run the section one. Yes, so it comes like this. We are writing complex formula. Check it. Then section one. This the P1 matrix is coming out over here like this. So the rank of P1. If we run it, rank of P1 will be less than 5. Rank of P1 comes out to be 4. Okay. What is a way to make it simpler? Yes. This is seeing that into shear transpose model. Shear transpose model is an entire volume. Okay. If I do this, now, 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 if I run this section, it is working. It is working. When I put in the next line, it's low. Let's read and this. Now let me run this section. Okay, it is what? Just we run like this. So overall, this is the P1 matrix, and we found the rank of P1 is less than 4. So let us do for observability matrix for output 2. So we can check. P matrix. for second order. This must be the same. It will be made P2, rank of P2. Where is 1? We replace it with 4. Mistake here. Transpose. Created. Plus 1, 2, 3, 4, 5. 1. Remember section again. We come on dot it. Let me exclude it. This is the final P1 matrix. Control like this, which is much larger. And if we find a rank of P1, it comes out to be 4. So there was an issue. I was using the same thing, I don't properly multiply. That was an error which was there. So now let us do the observability matrix for rank 2 for second output. So this will be P2. This is the second column, second column, second column, second column, second column. And this is P2. Okay, let us find out this. This is P2. And again, the rank of P2 comes out to be 4. So again, it is not observable for me 1 only. Okay, so system is not observable with delta VR bar alone. Okay. So let us find the observability for both outputs. Okay. Let us find P of P. This will be this also will be this also will be this also will be this also will be. So we run this section. We get the overall matrix to be like this. And the rank of P is 5. The rank of P comes out to be 5. So this is wrong. It is observable when both outputs are there, it is observable. Only when there's a single output, either of output 1 or output 2, it is not observable. So this also has been considered. So Sir has also done observability via auto. So auto test criterion also can be used. So eigenvalue lambda 3 equal to minus 0.5 is not observable delta Bn, and eigenvalue lambda 4 plus 0 with multiplicity of 2 is not observable by delta Bn bar. Okay, but together they are observable. If we consider both outputs, they are observable. So this module matching sir has shown in the vicinity of the operating point for various transient behavior conditions, through which we determine if our model is accurate. Okay, from the transient response, it is evident that the time variations of different variables obtained using the linear model are very close to those obtained from the nonlinear model, and the linear system is controllable and observable. This has been proven. So now we'll go to lecture 35. So what has happened here is the nonlinear mathematical model of the nuclear reactor was derived from first principles. The first principles are based on the physics of the system, then condition for the equilibrium of the system, and equilibrium values of different physical variables were derived. The linear model was derived, stability, controllability, and observability characteristics of the system examined, and the system is simulated to understand its transient behavior. Now, we will focus on linear output feedback of this one. And we are performing simulation of the nonlinear system with the linear output feedback to assess the transient behavior of the system to this lab. So all these are performed. So these are the differential equations, and these are the parameters of the system, and this is the steady state values, and this is the linearized model, and this is the outputs of the linearized model, and it is written in state space representation in this format. Which are the eigenvalues, it is controllable and observable based on the measurement of neutron density and its rate of change. If we measure neutron density and its rate of change, then my system is controlled. Then the system is controlled. Otherwise, only measuring neutron density or only measuring rate of change of neutron density is not sufficient to guarantee stability of the system. Then linear output feedback control design is considered. So we will consider the design of the linear model of this one. We call it G1. Okay, G is to be used. So to obtain, we have to ensure stability as well as good transient. It is a closed loop system matrix, which is A plus B JC. And is given in this form. And if we multiply it, we get our closed loop matrix to be given like this. So it can be seen that only two elements are altered. We cannot alter multiple elements. These two elements are capable of being altered. Okay, so let us just check. So let us run this. We will evaluate selection. Let us comment it out. So we are defining the gain matrix G1 and G2. And this is the closed loop matrix which we get. So this is the closed loop matrix, and if you observe, we can check with what Sir has got. Um, this is the overall closed loop matrix. Let us just verify. Minus beta upon L star lambda is 0. KP beta naught upon L star. Beta upon L star minus lambda triple 0. K upon tau n 0 minus 1 upon tau n 0 0. 0 0 minus KR upon tau r square minus 1 upon tau r 0. Then 0 0 K into G1 plus KR into K into G2 upon tau r. And then K in G2 0. So only these two elements are altered. Only these two elements are altered by the output feedback which we have considered. Okay. Now, let us say that I want to put my G1 at -10, G2 equal to -15. I want to see what is my, or let us find a better way. Let us find a characteristic volume. So here, volume, A underscore close. Volume, here volume, A underscore close to for this. We have from this section. Okay. This section. It comes out as raised to 5 plus s cubed plus s4 minus s plus s squared. So the characteristic polynomial comes out in this form. Okay. So what can be changed? You'll observe G2 can change s, and G1 can change s, and s square also can be changed. And this also can be changed. But there is very little scope of varying all the poles. Okay, all the coefficients of the characteristic polynomial cannot be changed by this way of output feedback. That is a limitation which we have. Okay. So that also we have seen. And now let us consider one case study where let us say my G1 value is -10 and G2 value is -15. And this is my closed loop polynomial. And I will have like beta, lambda, L star, all these things. I will substitute the values of G1, G2. And let us check what comes in. So let us run this section. All this has not been done. Let us run the entire script. So this is a closed loop numerator file, closed loop numeric polynomial. These are the values which are there, right? We will convert it to double. So this is in double format. And now we just find out the eigenvalues of this. So these are the eigenvalues. So there are certain limitations, like it is not particularly or completely state feedback, because we are only having the feedback of some states. We don't have the feedback of all the states, and because of that, we cannot perform, arbitrary pole placement. We cannot place all the poles as we desire. Like we cannot control each coefficient of the characteristic polynomial. But there are 2, 3 coefficients which can be controlled by the feedback of 2 states. And we have considered an example where we have considered -10, -50, etc. And we have used that to check whether the system is stable or not. It is found that the system is stable. Right? Okay, so this was also taught how when we vary G, how the pole locations also change. That also has been shown. And so let's consider gains -10 and -2.5. And the response of the closed loop behavior also has been shown. And this is also quite good. Right. the response also has been quite good. Okay, so let me write. This observability condition was uh, computed and derived using symbolic math program in MATLAB. So this is a very powerful tool, symbolic math toolbox. You can see that it is able to compute equations in the symbolic variables, which is very useful. So then we can substitute parameter values and then we can check it. Okay, so I've been really enjoying using this. It is being very useful for me and it is good for demonstrations, it is good for understanding, it is good for checking the accuracy of my expressions and derivations, etc. So this was done using observability condition was shown and observability depends on both the measurements. It is not sufficient to just measure the it is not sufficient to just measure the neutron flux density or the rate of change of the measured neutron flux density. They are not sufficient. Okay, we need to do both measurements are required. And if you try to understand, let me say this is my neutron flux density. It is passed, let us say this is ground minus plus or something. This is an amplifier. It's we have to get a low pass filter. It's not exactly an integrator. So how is the system response? Hmm. So we have an amplifier that gives my VN of t. That is passed through a differentiator. And that gives my VR of t. And that there is some mathematical manipulation and we get a VR bar of t. So this is a state, this is also a state, and this is also a state. So I don't know, perhaps the usage of all these states in certain conditions where system is observable to me if both outputs are measured. So this has to be checked. Further, this is similar to PD control. It's like a proportional plus derivative. Like a proportional plus derivative control can be seen over here. Okay. Because this is proportional to my meter of t, perhaps I have a reference and we are subtracting that, although those parts are not shown. So we have a proportional term and we have a derivative term. And we have a practical differentiator which has a time constant. And a practical differentiator will always be there because we cannot have an ideal differentiator. It's not physically realizable. So practical differentiator has a filter which will filter out the noise. Okay, so this is similar to PD, proportional derivative control, but there is no integral. There is no integrator present, so we don't know why an integrator is not required. Perhaps there's no tracking. Then we just check whether any tracking performance is showing. It is just showing the convergence, Bn of t, okay, Br of t, input signal also shown. Okay. So integrator tracking and regulation pro. So tracking is not shown. So no, best thing is to say reference is not considered. So the system performance with the reference is not shown. It's not considered in the simulations. In the simulations. So there is no integrator, but if we have a certain reference that we want the neutron flux density to be this much, or this must be the control, or the temperature must be regulated this much amount, or this much energy should be generated. If such constraints were there, then I have a feeling that an integrator would be required, would be needed. And this proportional derivative may not be sufficient. So these parts we will further consider. Let us see what further aspects are considered in the next week. So I'll give a brief recap of this session. So this is a recap. We have considered week 11, we have considered nuclear reactors. So this is, we are doing what is known as a case study. Case study of a nuclear reactor. And as Professor A.P. Tiwari works on these nuclear reactors, and he has been working on it for many decades, and he's an expert in these things. So he has considered this as an example, and he has found a mathematical model which is a non-linear. So I have to stress it is a non-linear. Since it is non-linear, it had to be linearized around a steady-state operating point. So linearization was done. Then it was checked whether the linearized state-space model is controllable or observable. And these were controllable and observable only if theta naught should be greater than zero. That is, the neutron flux density should be positive, should not be zero. If the neutron flux density is zero, we cannot control it, we cannot observe it. What happens during startup conditions, etc., I will discuss and not considered here. But for our understanding, for getting a grasp of these fundamental concepts applied to an actual real world practical system is shown. Okay, this mathematical model has various assumptions, and it is like a generalized model which it is like a lumped model express considered, but it is very good for for getting into for starting the understanding of these nuclear reactors. So I also discussed about the various nuclear reactors, as well as what coolants are used and how much energy is generated in nuclear fission, as well as how 2 to 3 neutrons are released. And there are 4 research nuclear reactors in India, 2 at Kalpakkam and 2 in BARC Trombay in Mumbai, right? So there are various details which you can try to remember, try to understand. Then the mathematical modeling of is done. What is the rate of change of neutron density? What is the rate of change of delayed neutron precursors is considered? Because there are 2 types of neutrons. One is the fast neutrons, one is the delayed neutrons. So what is the measurement of neutron flux density? It's also shown how in an actual system we need a sensor. We need to measure how much is the flux density of the neutron. Because basically that is only what is going to control how much energy is going to be produced, etc. Measurement of neutron flux density is shown. There's a measurement of rate of change of neutron density, which is considered. So, what is the measured neutron flux density? We are doing a differentiation of them to get what is the approximate or the estimated rate of change of the actual neutron flux density in the reactor. So, we are not actually getting the neutron flux density, the rate of change of neutron flux density in the reactor, measurement of that. We are taking a derivative of the measured neutron flux density. So there is a slight error. It is not exactly that because of the first order response of the measurement of the neutron flux density. So it is not exactly that, right? And due to this, there is a certain, what you say, this is a linear combination of a state and the derivative of a state. So what sir has done is some mathematical mod mathematical uh, manipulation has been done, performed, mathematical manipulation performed to make it linear combination of states. You write it as linear combination of states. So I think this is a general practice, a well-known standard practice which is used in industry. Then what is the reactivity variations also has been shown. And the overall set of equations is shown where the non-linearity, where the linear equations are written. Then what is the input? This is my input. And these are the output equations. These are some additional set of equations. Model linearization is performed. Because it is a non-linear model, we find a linearized model around the steady state operating point. And based on that, we check the controllability condition was checked and the observability condition also was checked. We checked it in MATLAB and we saw that observability depends on both the measurements, and it is not sufficient to just measure the neutron flux density or the rate of change of the measured neutron flux density. As well as we consider an example of output feedback control to stabilize the system. Okay, how we get the matrix is A plus B G into C, where this is the gain matrix, right? So this is a different way to place the poles. We cannot, so here arbitrary pole placement is not possible. So here arbitrary pole placement is not possible. That is, we cannot shift or control all the poles. There are certain poles which we can shift, certain poles which we cannot shift, right? Okay, so various overall linearized plan model was shown. The observability condition was derived, and we found the transpose and how there are different ways. Because we use the duality principle where we can find observability by finding the controllability of A transpose, C transpose, right? We did a partitioning of the system, and then we found the controllability. And then we found the observability matrix for the first output, observability matrix for the second output. We found their ranks are 4, that is, they are rank deficient. So they are not a full rank, so it is not completely observable. But then we found the observability matrix when we considered both the outputs, and it was found to be full rank. So the system is observable if we can observe both the states, and the condition is that if meter naught, that is the neutron flux density, that is the average of steady state neutron flux density is greater than 0, then the system is both observable and controllable was also shown. Then we use these parameter values, and then we found our gain matrix G1, G2, which we considered. This is the overall closed loop matrix, and we see that only two coefficients, only two variables, only two elements can be changed by G1 and G2. And then we saw the characteristic polynomial, and again, if you observe the characteristic polynomial, only the S term and the S squared term and the last constant term can be changed, can be controlled, or can be changed by choice of G1 and G2. Okay, the S raised to S and the S raised to 4 and S raised to 3. These terms we cannot change the coefficients of those terms. Okay, and then we selected some G1, G2, some certain values. We found this is the closed loop. Let us just consider case when G1 is 1 and G2 let us consider to be 0. Or let us make it also 1. Let us see whether it is stable. The poles are stable in that case. Okay, but this pole is not, one pole is not stable. So let us make G2 0. Now again this is not stable. So if we make it -1, now we're stable, but this is again positive, so this is not positive. So let us do G1 -5 and G2 -1. So if I when G1, G2 are positive, it is not possible to stabilize it. We need negative feedback. Kind of like the gain values like probably this is the consideration for need for negative feedback. And this positive feedback is becoming unstable. But probably we have to do a thorough lot of the locus of the pole locations will be required to exactly check. Okay. So I thank you for joining the session. I'll end it. Good night.